Hello, my name is Pan Nie, and I'm a second-year PhD student from the Electrical Computer Engineering Department at McMaster University. Today, I'm going to present the paper and the recent completed project organized by Professor Nigel Schofield, Dr. Matthias Prado, and myself. The topic today is the SVM strategies for multi-phase voltage source inverters. So today I will talk about the potential multi-phase system applications and the generalized multi-phase system stationary coordinate transformation, the space vector modulation SVM strategies studies, simulation and experiment results, comparison, evaluation, and validation, conclusions, references, and acknowledgement. So the machine drive applications covers a variety of fields, including, but not restriction of the hybrid electrical vehicles like Toyota Prius, the full electrical vehicles like Tesla, the aerospace actuators and generation systems like the multi-phase drive systems, multi-phase machine drive systems used in Airbus A380 or Boeing 787. And traction systems on more electrical ship like Queen's Mary 2 cruise or the aircraft Elizabeth II of Royal Navy. Independent of the applications, however, the AC drive systems is more widely used than the DC counterparts. Among the AC driving systems, it is the three-phase systems that are normally widely, technically, commercially mature and be widely used. Due to the application and implementation of the power converters and also not the direct online operation, it's not necessary to use the three-phase systems. So we can use the onboard power electronics to achieve the multi-phase systems like three-phase, five-phase, six-phase, seven-phase, nine-phase, or even higher phase numbers. Compared with the three-phase systems, the multi-phase system can decrease the per-phase rating, increase the fault tolerance capability, and improve the torque output quality. In this paper, we proposed a generalized SVM strategies, and there are 4 different SVM strategies, including the first one is the symmetrical SVM. The second one is the discontinuous SVM. The third one is group-based SVM. And the fourth one is the selective active voltage vector SVM. We also set a sinusoidal pulse-wise modulation as a benchmark to compare with the different SVM strategies. So let's turn to the generalized multi-phase stationary coordinate transformation. Vector space decomposition, VSD, this method is used to simplify and decompose the n-phase system into a set of zero sequence planes and k mutual orthogonal planes, where k is given by k equals to n-1/2, where n is the phase number. The general clock's decoupling transformation matrix is given by this equation. And x1, y1 plane contains the n times h plus minus 1 harmonics, where the h is even. And x2, y2 plane contains the n times h plus minus 2 harmonics, where the h is odd. To the xk, yk plane, it contains the harmonics n times h plus minus k, where the h is odd when k is odd and h is even when k is even. Alpha equals to 2 pi over the phase number of this system. So due to the different conditions, we have a different scalar m. For the power invariant conditions, m equals to square 2 over n, and for the amplitude invariant conditions, m equals 2 over n. Here, we assume the start connection of the machine, and if the phase number is odd, there is no zero sequence components in this system. And if the phase number is even, there are zero sequence components in these systems. The space vector modulation strategy studies. In a two-level multi-phase voltage source inverter, if there are n lags, there is 2 times n switches and 2 to the power n different switching states corresponding to 2 to the power n different voltage vector, possible voltage vectors. In this paper, we use a 9-phase brushless permanent magnet machine drive system to simulate and validate the theoretical study. There are 2 different connection topologies. The first topology is a 9-phase star connection. There is only one star. All the 9 phases go to one neutral point. This topology is for the SVM strategies, except the group-based SVM strategy. The second topology is group-based 3 times 3 phase star connection topology, where we have 3 separate SVM schemes, and there are 3 separate neutral points here. There are 3 stars here. This is the synthesized equations for the synthesized voltage vector equations for the SVM strategy. It's not new. And for the figure 6a shows the combination of 3 times 3 phase systems to make a 9-phase systems. In the conventional 3 systems, the phase displacement between successive phase is 120 degrees. If we shift the 3-phase system to by 40 degree electrical, we can get the second side of 3-phase system. And if we continue to shift the system by 40 degree, we can get the third side of 3-phase systems. And these 3-phase systems are combined to make one 9-phase systems. The figure 6b shows the voltage, the synthesized voltage vector, and the figure 6c shows the synthesized voltage vector, which are categorized into 4 different groups in terms of their magnitude, in terms of their different magnitudes. For the symmetrical and discontinuous SVM strategies, the first, we derive the duty ratios for phase N under the SPWM strategy, which is duty ratio 1 to duty ratio N here. And we also calculate the maximum of the duty ratio and the minimum of the duty ratio. For the N-phase symmetrical SVM, the phase N duty ratio equals to the duty ratio, the phase N duty ratio under the SPWM strategy, and plus the combination of the maximum and minimum values. And the N-phase discontinuous SVM can be shown in these equations. So figure 7 shows the duty ratio of the phase voltage for 3-phase system and the 9-phase system, both for the symmetrical and the discontinuous SVM strategies based on this method. And table 1 shows the comparisons of the maximum modulation index under different strategies. Sinusoidal as the benchmark, the symmetrical discontinuous SVM, the proposed one, the SVM with the selected voltage vectors, the other proposed strategies. So we do the simulation, and experiment shows the results to do the comparison between different strategies, do the evaluation, and validate our theoretical study. We use the TMS320F28377D DSP, which is a dual-core DSP from Texas Instruments. 3 IGBTs IPM, intelligent power module, which for each one is a 3-phase 4-bridge IGBT to make a 9-phase system. The corresponding driver boards, the power supplies and accessory circuit boards for measurement and detection. This is the overall of the setup. This is the 9-phase inverter. This is the control part and accessory board part. This is the machine, 9-phase BLPM, and this is the load machine. And here we show the phase voltage and phase current under different SVM strategies. For each strategies, we have the simulation result and also the experiment result to validate the simulation and also the theoretical study. As you can see here, the symmetrical SVM simulation, the blue one is the voltage, the phase voltage, and the black one is the phase current. Figure 9b shows the corresponding experiment result, which match the figure 1a, the simulation result. Also, we do the fast Fourier transformation to analyze the phase voltage. And we select 2 windows. One is high frequency range, and the other is lower frequency range. The high frequency range from 0 Hz to 25 kilohertz to investigate and study the frequency at the switching frequency and the integer number of switching frequency, or higher than the frequency higher than the switching frequency. And also we investigate the lower frequency range of the voltage spectra of the phase voltage. So this picture shows both the simulation. The blue line is the simulation result of the FFT analysis, and the red ones are for the experiment result, and they match with each other. So finally, we draw the conclusions. We proposed the generalized N-phase system SVM strategies. We implement it and validate by a 9-phase VSI and BLPM drive system through the simulations and experiments. So among these strategies, 3 times the 3-phase SVM has the best performance with the compromise of voltage harmonic contents, current or voltage THD, total harmonic distortion, and modulation index. The symmetrical SVM comes the second with the modulation index 0.508, which has less harmonic content in both the lower and higher frequency range than discontinuous SVM. However, the discontinuous SVM strategy has less switching events, which is related to the switching losses. This is less than the symmetrical SVM. So this is the trade-off during the design between the power losses in the inverter and the machine. So these strategies can achieve the improved torque output than the SVM Group D, which is a selective active voltage vector SVM. So despite the highest maximum modulation index that SVM Group D can achieve, this strategy has much higher harmonic content in the lower frequency range and the current total harmonic distortion, resulting in high torque ripple and machine couple losses. The table 2 shows the comparisons between different switch schemes in terms of the current THD and voltage THD, both for the simulation and experiment results. And from the table, you can see they match with each other as well. So during the research, we have references from multiphase machines from Professor Nigel Schofield, and I also refer some paper from the SVM strategy from Professor Amy Levy from Liverpool Moral University. Also, we refer the PhD thesis from Dr. Matthias Prado. So here, the authors acknowledge the Canada Excellent Research Chair Program, Natural Science and Engineering Research Council of Canada, Automotive Partnership Canada for support of Mr. Nie, myself, the PhD studentship. Thank you very much, and any questions are welcome.
Hello, Obre Georgievich from Liverpool John Moores University. So, would you please better emphasize what is actually novelty of this paper, because I don't see it, honestly. So would you tell me exactly what is new that you did?
Pardon me?
Okay, so I think that generalized multiphase space vector modulation, that it's already been solved problem. So would you once again tell me which part of the paper, which modulation strategies are new here? Okay, and the second, just like a comment, which is general comment, not directly related to your presentation. I think that it's unfair to compare space vector modulation strategies with a sinusoidal PWM without min-max injection. It's related, I would say it's just like a general comment, not only for your presentation. Okay, thank you.
Okay, I will answer your first question and then can you repeat your second question. So my answer for the first question is there are some switching schemes for the multiphase machine, yes. However, no publication has been issued for the comparison, evaluation for the performance difference between different switching strategies. So, and also they focus on the specific phase numbers of the multi-phase systems like 5-phase, 7-phase, or even more phase numbers. In my project, in this paper, we generalized the methodology, and this is one, probably, I think, one novel point. The second one is we compare different possible switching schemes and evaluate their individual performance and compare their differences. Yeah, actually, there are a lot of possibilities, more schemes to achieve the multi-phase switching schemes. So what we proposed here is just some of them, and we can do more, or we can do more in the future, and also we combine the other part analysis of the multi-phase inverter systems. We can combine the oh yeah, this is out of the topic. Then can you repeat your second question, please? Yeah.
Okay, so the second part was actually not a question, it was just a comment that for fair comparison with space vectors, sinusoidal PWM with min-max injection should be used, in my view. Okay, so that's just a comment. Thank you for your first answer.
For the second question, do you mean
It's not a question. It's not a question. Thank you.
It's fine. Yeah. It was only comment. Yeah.
Oh, yeah. So for the sinusoidal PWM strategy.
Yeah, that's perfectly fine. Yeah. Thank you. Yeah. Okay. Thank you.